Alkaline earth metal. The alkaline earth metals are 6 chemical elements in group 2 of the periodic table. They are beryllium, magnesium, calcium, strontium, barium, and radium. The elements have very similar properties. They are all shiny, silvery white, somewhat reactive metals at standard temperature and pressure. Structurally, they have in common an outer s electron shell which is full. That is, this orbital contains its full complement of 2 electrons, which these elements readily lose to form cations with charge +2, and an oxidation state of +2. All the discovered alkaline earth metals occur in nature, although radium occurs only through the decay chain of uranium and thorium and not as a primordial element. Experiments have been conducted to attempt the synthesis of element 120, the next potential member of the group, but they have all met with failure. As with other groups, the members of this family show patterns in their electronic configuration, especially the outermost shells, resulting in trends in chemical behavior. Most of the chemistry has been observed only for the first 5 members of the group. The chemistry of radium is not well established due to its radioactivity, thus, the presentation of its properties here is limited. The alkaline earth metals are all silver-colored and soft, and have relatively low densities, melting points, and boiling points. In chemical terms, all of the alkaline metals react with the halogens to form the alkaline earth metal halides, all of which are ionic crystalline compounds. All the alkaline earth metals except beryllium also react with water to form strongly alkaline hydroxides and, thus, should be handled with great care. The heavier alkaline earth metals react more vigorously than the lighter ones. The alkaline metals have the second lowest first ionization energies in their respective periods of the periodic table because of their somewhat low effective nuclear charges and the ability to attain a full outer shell configuration by losing just 2 electrons. The second ionization energy of all of the alkaline metals is also somewhat low. Beryllium is an exception. It does not react with water or steam, and its halides are covalent. If beryllium did form compounds with an ionization state of +2, it would polarize electron clouds that are near it very strongly and would cause extensive orbital overlap, since beryllium has a high charge density. All compounds that include beryllium have a covalent bond. Even the compound beryllium fluoride, which is the most ionic beryllium compound, has a low melting point and a low electrical conductivity when melted. All the alkaline earth metals have 2 electrons in their valence shell, so the energetically preferred state of achieving a filled electron shell is to lose 2 electrons to form doubly charged positive ions. The alkaline earth metals all react with the halogens to form ionic halides, such as calcium chloride, as well as reacting with oxygen to form oxides such as strontium oxide. Calcium, strontium, and barium react with water to produce hydrogen gas and their respective hydroxides, and also undergo transmetallation reactions to exchange ligands. Calcium, strontium, and barium all form octocarbonyl complexes in an 18-electron valence shell. The compounds were characterized in frozen neon matrices by vibrational spectroscopy and in gas phase by mass spectrometry. Analysis of the electronic structure reveals that not only barium but also strontium and calcium may effectively use their diatomic orbitals in chemical bonding, suggesting they behave like transition metals. The table below is a summary of the key physical and atomic properties of the alkaline earth metals. Of the 6 alkaline earth metals, beryllium, calcium, barium, and radium have at least one naturally occurring radioisotope. Magnesium and strontium do not. Beryllium 7, beryllium 10, and calcium 41 are trace radioisotopes. Calcium 48 and barium 130 have very long half-lives and thus occur naturally on Earth, and all isotopes of radium are radioactive. Calcium 48 is the lightest nuclide to undergo double beta decay. Calcium and barium are weakly radioactive. Calcium contains about 0.1874% calcium 48, and barium contains about 0.1062% barium 130. The alkaline earth metals are named after their oxides, the alkaline earths, whose old-fashioned names were beryllia, magnesia, lime, strontia, and baryta. These oxides are basic when combined with water. Earth is an old term applied by early chemists to nonmetallic substances that are insoluble in water and resistant to heating, properties shared by these oxides. The realization that these earths were not elements but compounds is attributed to the chemist Antoine Lavoisier. In his Traité élémentaire de chimie of 1789 he called them salt-forming earth elements. Later, he suggested that the alkaline earths might be metal oxides, but admitted that this was mere conjecture. In 1808, acting on Lavoisier's idea, Humphrey Davy became the first to obtain samples of the metals by electrolysis of their molten earths, thus supporting Lavoisier's hypothesis and causing the group to be named the alkaline earth metals. The calcium compounds calcite and lime have been known and used since prehistoric times. The same is true for the beryllium compounds beryl and emerald. The other compounds of the alkaline earth metals were discovered starting in the early 15th century. The magnesium compound magnesium sulfate was first discovered in 1618 by a farmer at Epsom in England. Strontium carbonate was discovered in minerals in the Scottish village of Strontium in 1790. The last element is the least abundant, radioactive radium, which was extracted from uraninite in 1898. All elements except beryllium were isolated by electrolysis of molten compounds. Magnesium, calcium, and strontium were first produced by Humphrey Davy in 1808, whereas beryllium was independently isolated by Friedrich Wöhler and Antoine Bussy in 1828 by reacting beryllium compounds with potassium. In 1910, radium was isolated as a pure metal by Curie and André-Louis Debierne, also by electrolysis. Beryl, a mineral that contains beryllium, has been known since the time of the Ptolemaic kingdom in Egypt. Although it was originally thought that beryl was an aluminium silicate, beryl was later found to contain a then unknown element when, in 1797, Louis Nicolas Vauquelin dissolved aluminium hydroxide from beryl in an alkali. In 1828, Friedrich Wöhler and Antoine Bussy independently isolated this new element, beryllium, by the same method, which involved a reaction of beryllium chloride with metallic potassium. This reaction was not able to produce large ingots of beryllium. It was not until 1898, when Paul Leboeuf performed an electrolysis of a mixture of beryllium fluoride and sodium fluoride, that large pure samples of beryllium were produced. Magnesium was first produced by Sir Humphrey Davy in England in 1808 using electrolysis of a mixture of magnesia and mercuric oxide. Antoine Bussy prepared it in coherent form in 1831. Davy's first suggestion for a name was magnium, but the name magnesium is now used. Lime has been used as a material for building since 7000 to 14,000 BCE. And kilns used for lime have been dated to 2500 BCE in Kefahah, Mesopotamia. Calcium as a material has been known since at least the 1st century, as the ancient Romans were known to have used calcium oxide by preparing it from lime. Calcium sulfate has been known to be able to set broken bones since the 10th century. Calcium itself, however, was not isolated until 1808, when Humphrey Davy, in England, used electrolysis on a mixture of lime and mercuric oxide, after hearing that Johannes Jacob Berzelius had prepared a calcium amalgam from the electrolysis of lime and mercury. In 1790, physician Adair Crawford discovered ores with distinctive properties, which were named strontites in 1793 by Thomas Charles Hope, a chemistry professor at the University of Glasgow, who confirmed Crawford's discovery. Strontium was eventually isolated in 1808 by Sir Humphrey Davy by electrolysis of a mixture of strontium chloride and mercuric oxide. The discovery was announced by Davy on June 30, 1808 at a lecture to the Royal Society. Barite, a mineral containing barium, was first recognized as containing a new element in 1774 by Carl Scheele, although he was able to isolate only barium oxide. Barium oxide was isolated again 2 years later by Johann Gottlieb Gahn. Later in the 18th century, William Withering noticed a heavy mineral in the Cumberland lead mines, which are now known to contain barium. Barium itself was finally isolated in 1808 when Sir Humphrey Davy used electrolysis with molten salts, and Davy named the element barium, after baryta. Later, Robert Bunsen and Augustus Matheson isolated pure barium by electrolysis of a mixture of barium chloride and ammonium chloride. While studying uraninite, on December 21, 1898, Marie and Pierre Curie discovered that, even after uranium had decayed, the material created was still radioactive. The material behaved somewhat similarly to barium compounds, although some properties, such as the color of the flame test and spectral lines, were much different. They announced the discovery of a new element on December 26, 1898 to the French Academy of Sciences. Radium was named in 1899 from the word radius, meaning ray, as radium emitted power in the form of rays. Beryllium occurs in the Earth's crust at a concentration of 2 to 6 parts per million, much of which is in soils, where it has a concentration of 6 ppm. Beryllium is one of the rarest elements in seawater, even rarer than elements such as scandium, with a concentration of 0.2 parts per trillion. However, in fresh water, beryllium is somewhat more common, with a concentration of 0.1 parts per billion. Magnesium and calcium are very common in the Earth's crust, being respectively the 5th/8th most abundant elements. None of the alkaline earth metals are found in their elemental state. Common magnesium-containing minerals are carnallite, magnesite, and dolomite. Common calcium-containing minerals are chalk, limestone, gypsum, and anhydrite. Strontium is the 15th most abundant element in the Earth's crust. The principal minerals are celestite and strontianite. Barium is slightly less common, much of it in the mineral barite. Radium, being a decay product of uranium, is found in all uranium-bearing ores. Due to its relatively short half-life, radium from the Earth's early history has decayed, and present-day samples have all come from the much slower decay of uranium. Most beryllium is extracted from beryllium hydroxide. One production method is sintering, done by mixing beryl, sodium fluorosilicate, and soda at high temperatures to form sodium fluoroberylate, aluminium oxide, and silicon dioxide. A solution of sodium fluoroberylate and sodium hydroxide in water is then used to form beryllium hydroxide by precipitation. Alternatively, in the melt method, powdered beryl is heated to high temperature, cooled with water, then heated again slightly in sulfuric acid, eventually yielding beryllium hydroxide. The beryllium hydroxide from either method then produces beryllium fluoride and beryllium chloride through a somewhat long process. Electrolysis or heating of these compounds can then produce beryllium. In general, strontium carbonate is extracted from the mineral celestite through two methods, by leaching the celestite with sodium carbonate, or in a more complicated way involving coal. To produce barium, barite is subjected to barium sulfide by carbothermic reduction, which is dissolved with other elements to form other compounds, such as barium nitrate. These in turn are thermally decompressed into barium oxide, which eventually yields pure barium after a reaction with aluminium. The most important supplier of barium is China, which produces more than 50% of world supply. Beryllium is used mostly for military applications, but there are other uses of beryllium, as well. In electronics, beryllium is used as a p-type dopant in some semiconductors, and beryllium oxide is used as a high-strength electrical insulator and heat conductor. Due to its light weight and other properties, beryllium is also used in mechanics when stiffness, light weight, and dimensional stability are required at wide temperature ranges. Magnesium has many uses. It offers advantages over other materials such as aluminium, although this usage has fallen out of favor due to magnesium's flammability. Magnesium is also often alloyed with aluminium or zinc to form materials with more desirable properties than any pure metal. Magnesium has many other uses in industrial applications, such as having a role in the production of iron and steel, and the production of titanium. Calcium also has many uses. One of its uses is as a reducing agent in the separation of other metals from ore, such as uranium. It is also used in the production of the alloys of many metals, such as aluminium and copper alloys, and is also used to deoxidize alloys as well. Calcium also has a role in the making of cheese, mortars, and cement. Strontium and barium do not have as many applications as the lighter alkaline earth metals, but still have uses. Strontium carbonate is often used in the manufacturing of red fireworks, and pure strontium is used in the study of neurotransmitter release in neurons. Barium has some use in vacuum tubes to remove gases, and barium sulfate has many uses in the petroleum industry, as well as other industries. Due to its radioactivity, radium no longer has many applications, but it used to have many. Radium used to be used often in luminous paints, although this use was stopped after workers got sick. As people used to think that radioactivity was a good thing, radium used to be added to drinking water, toothpaste, and many other products, although they are also not used anymore due to their health effects. Radium is no longer even used for its radioactive properties, as there are more powerful and safer emitters than radium. Magnesium and calcium are ubiquitous and essential to all known living organisms. They are involved in more than one role, with, for example, magnesium or calcium ion pumps playing a role in some cellular processes, magnesium functioning as the active center in some enzymes, and calcium salts taking a structural role, most notably in bones. Strontium plays an important role in marine aquatic life, especially hard corals, which use strontium to build their exoskeletons. It and barium have some uses in medicine, for example barium meals in radiographic imaging, whilst strontium compounds are employed in some toothpastes. Excessive amounts of strontium-90 are toxic due to its radioactivity, and strontium-90 mimics calcium and then can kill. Beryllium and radium, however, are toxic. Beryllium's low aqueous solubility means it is rarely available to biological systems, it has no known role in living organisms and, when encountered by them, is usually highly toxic. Radium has a low availability and is highly radioactive, making it toxic to life. The next alkaline earth metal after radium is thought to be element 120, although this may not be true due to relativistic effects. The synthesis of element 120 was first attempted in March 2007, when a team at the Fleroff Laboratory of Nuclear Reactions in Dubna bombarded plutonium-244 with iron-58 ions. However, no atoms were produced, leading to a limit of 400 Fb for the cross-section at the energy studied. In April 2007, a team at the GSI attempted to create element 120 by bombarding uranium-238 with nickel-64, although no atoms were detected, leading to a limit of 1.6 Pb for the reaction. Synthesis was again attempted at higher sensitivities, although no atoms were detected. Other reactions have been tried, although all have been met with failure. The chemistry of element 120 is predicted to be closer to that of calcium or strontium instead of barium or radium. This is unusual, as periodic trends would predict element 120 to be more reactive than barium and radium. This lowered reactivity is due to the expected energies of element 120's valence electrons, increasing element 120's ionization energy and decreasing the metallic and ionic radii.